Welcome to a lesson on solving constant coefficient second-order linear homogeneous differential equations. The equation a times y double prime plus b times y prime plus c times y equals 0 with constants a, b, and c that do not depend on x is a linear second-order homogeneous equation with constant coefficients. Let's start by looking at an example. Let's consider the given initial value problem. Analyzing the differential equation, notice we have a equals 1, b equals -6, and c equals 8. To guess a solution, we want to think of a function that stays essentially the same when we differentiate it, so that we can take the function and its derivatives, add some multiples of each other, and end up with 0. This should remind us of the exponential function. Let's try y equals e to the power of rx, where applying the chain rule, y prime is equal to r times e to the power of rx, and y double prime is equal to r squared times e to the power of rx. Performing substitution into the differential equation, we have the second line here, and if we divide through by e to the power of rx, we get the quadratic equation r squared minus 6r plus 8 equals 0, which we can solve by factoring, giving us r equals 2 or r equals 4. Subbing 2 for r and 4 for r, we now know two solutions. One solution is y1 equals e to the power of 2x, and a second solution is y2 equals e to the power of 4x. And these two functions are linearly independent. If they were not linearly independent or dependent, we could write one as a multiple of the other, where if c is some constant, we would have e to the power of 4x equals c times e to the power of 2x. And if we divide e to the power of 4x by e to the power of 2x, which I've shown below, notice how we don't get a constant, which verifies the two functions are linearly independent, and therefore the general solution would be the linear combinations of the two solutions, meaning the general solution is y equals c sub 1 times e to the power of 2x plus c sub 2 times e to the power of 4x. And now we need to determine c sub 1 and c sub 2 using the initial conditions, which I've shown here again in blue on the left. Before we do this, though, we have to find y prime. Applying the chain rule, we have y prime equals 2 c sub 1 e to the power of 2x plus 4 c sub 2 times e to the power of 4x. And now we perform substitution using the initial conditions, which gives us -2 equals y sub 0, which is c sub 1 plus c sub 2, again because x is 0 and e to the 0 is 1. And we also have 6 equals y prime of 0, which gives us 6 equals 2 times c sub 1 plus 4 times c sub 2, again because e to the power of 0 is 1. And now we need to solve the system to determine c sub 1 and c sub 2. For example, we can divide the second equation by 2, which gives us 3 equals c sub 1 plus 2c sub 2, and then subtract the two equations, which I've shown here below. Subtracting the two equations gives us -5 equals -c sub 2, and therefore c sub 2 is equal to 5. And now we can determine c sub 1 by performing substitution. Using the first equation, if we substitute 5 for c sub 2, we have -2 equals c sub 1 plus 5, which gives us c sub 1 equals -7, and therefore the particular solution is y equals -7 e to the power of 2x plus 5 times e to the power of 4x. When we solve a linear second-order homogeneous differential equation with constant coefficients in this form here, ar squared plus br plus c equals 0 is called the characteristic equation, and when we solve this equation, there are three possible outcomes. We just saw the first case where r1 and r2 are two distinct real roots, and therefore the general solution is y of x equals c sub 1 times e to the power of r sub 1x plus c sub 2 times e to the power of r sub 2x. If we get two real equal roots or solutions, then the general solution is a little bit different. Notice how the second term has an extra factor of x. We'll look at this example next, and then finally, if r sub 1 and r sub 2, the roots or solutions to the characteristic equation are complex, then the general solution is in the form shown here at the bottom, where y of x equals c sub 1 times e to the power of alpha x cosine beta x plus c sub 2 times e to the power of alpha x times sine of beta x. Let's look at some more examples. Here we're asked to find the general solution to the given differential equation, where notice a is equal to 1, b is equal to -8, and c is equal to 16, which means the characteristic equation is r squared minus 8r plus 16 equals 0. This is actually a perfect square trinomial where the two factors are r minus 4. And therefore we have a double solution or double root indicating r sub 1 and r sub 2 are both equal to 4. And therefore the general solution is y equals c sub 1 times e to the power of 4x plus c sub 2 x times e to the power of 4x. Again, we have this extra factor of x here because we have a repeated root or two equal roots. Remember, this indicates that one solution is y1 equals e to the power of 4x, and a second solution is y2 equals x times e to the power of 4x. Let's verify that y2 equals x times e to the power of 4x is a solution to the differential equation. To do this, we'll have to find y prime and y double prime, which does require the chain rule and the product rule. Y prime is equal to e to the power of 4x plus 4x times e to the power of 4x, and y double prime is equal to 8 e to the power of 4x plus 16x e to the power of 4x. Performing substitution into the differential equation does verify y2 equals x e to the power of 4x is a solution to the differential equation. And now let's look at one more example where the solution to the characteristic equation is complex. So we're trying to find the general solution to the given initial value problem. The characteristic equation is r squared minus 6r plus 13 equals 0. We can solve this by completing the square, or I've also shown in blue on the right the quadratic formula. The solutions are r equals 3 plus or minus 2i. So using case 3 in our notes below, we now know that alpha is equal to 3 and beta is equal to 2. Which means the general solution is y equals c sub 1 e to the power of 3x cosine 2x plus c sub 2 e to the power of 3x times sine 2x. And now we need to determine c sub 1 and c sub 2 using the initial conditions. Let's first use the condition y of 0 equals 0, indicating we substitute 0 for x and 0 for y. Simplifying, sine 0 is 0, giving us c sub 1 is equal to 0. And if c sub 1 is equal to 0, we now know that y is equal to c sub 2 e to the power of 3x sine 2x, which we need to differentiate in order to use the second initial condition of y prime of 0 equals 10, which again requires the product rule and the chain rule. You may want to pause the video and verify this. Y prime is equal to 3 c sub 2 e to the power of 3x sine 2x plus 2 c sub 2 e to the power of 3x cosine 2x. And now we substitute 0 for x and 10 for y prime, which will give us 10 equals 2 times c sub 2, and therefore c sub 2 equals 5. Indicating the particular solution is y equals 5 times e to the power of 3x sine 2x. We will go ahead and stop here, but I'll leave you with the following notes. I hope you found this helpful.